Okay, so for the last stop of the workshop, and today, Piotr Hajac is going to talk us about Unital embeddings, sister algebra that one can see. One can see the sister algebra in the Unital embeddings.
Thank you very much, Gilles. As I was mentioning earlier, but it was off the record, I owe this beautiful title to Francesco, who helped me invent it. And indeed, what you can see here are both sister algebras and the Unital embeddings. And this is really the main point of my talk. Let me first start by posing a problem. Everybody knows Kunz algebras, and they're already defined today. So let me skip it. Let me ask the following very natural question. When do we have a unital star homomorphism from OM to OM? You see, Kunz algebras are simple, so any star homomorphism must be an embedding, all right? Because the only possible kernel is 0. And now, if you look at the K-theory, then you see that the K-theory of ON is just the torsion group of rank n-1, and the class of one in the algebra, one algebra viewed as a projective module, is one in the cyclic group, okay? And what you immediately can conclude from this calculation of K-theory, K1 is 0, so it's irrelevant, is that if there exists a unital star homomorphism from ON to OM, I should take my highlighter, okay. Yeah, if there exists a unital star homomorphism from ON to OM, I should do it here, right? Ah, wonderful, yeah. Then M and N must satisfy this congruence relation. And that's obvious from what I wrote above, because if you have something which is 0 modulo m-1, well, I mean, you have to map 0 to 0. So if you really look at the cyclic groups and remember that the class of 1 is 1, you immediately see that this congruence relation must be satisfied. Okay. Yeah, I mean, you have to be 0. If you are 0 modulo m-1, you better be 0 modulo n-1, which gives you this number k. Anyway, this is just elementary number theory. And you have a theorem of Kirchberg and Phillips that tells you that if you have nice, simple sister algebras, which have the same K-theory groups and have the same class of 1, that they must be, sorry, no. Sorry, they must be isomorphic, but the theorem is stronger. If you look at appropriate simple sister algebras and K-theory allows for a star homomorphism between them, then the star homomorphism in fact exists. This is highly non-trivial statement, because it means that you can lift the homomorphism that you have at the level of K-theory with a preservation of the class of 1, that if you have it, then you can lift it to a star homomorphism between these simple sister algebras. But it's a non-constructive theorem. It tells you that such a star homomorphism exists, but it doesn't tell you what it looks like. And in 2009, Kawamura provided a very explicit formula for an embedding of Kunz algebras, okay? And so whenever this congruence relation is satisfied, Kawamura gives you an explicit formula for this embedding. And what I want to explain to you later on is that this Kawamura's explicit formula can be derived very easily from our theory of functorial induction of star homomorphisms from morphisms of graphs. Okay, but this later on. To begin with, okay, I want to now, so that is what was known. Now I want to pose a problem. You see, I was visiting Jack Spielberg in Arizona together with Mariusz Tobolski, and we just developed the concept of locally derived graphs, and we're doing examples, and we applied our locally derived graph construction to the Kunz graph O2, so the Hawaiian earring with 2 loops. And it gave us some strange graph. By computing the K-theory, we knew that it was Morita equivalent to O3, but we didn't know exactly what it was. But when Jack Spielberg saw the graph, he immediately said, well, come on, these are 2x2 matrices over O3. So this way, we incidentally bumped into an embedding. Oh, now I have to change, I have to change this to this, okay. Now I can write. No, I still didn't change it. Okay, now it works. We incidentally bumped into the embedding of O2 in M2 of O3. Okay. And it was nice because we could write it down in terms of, it was induced from a graph homomorphism. So we had a graph homomorphism, and contravariantly, it induced this embedding of O2 into M2O3. But then, of course, we couldn't resist asking the general question. What if we have arbitrary P, arbitrary Q, and arbitrary K? Well, again, just from the K theory, you can see that the congruence relation that you must satisfy, now I want to go back to my highlighter, yes, is this one. Oops, I forgot. I have a touchscreen on my laptop, so it's okay, it's this one. It's slightly more general now because now we have three natural numbers, P, K, and Q. They're independent natural numbers. And you're asking for which triples of natural numbers the K theory allows you such an embedding. Well, and the answer is very simple. It allows you such an embedding if and only if this congruence relation is satisfied. So now your free variable is S. It's a non-negative natural number. And well, you basically, again, do the K theory. Of course, MK of OQ is Morita equivalent to OQ, so it has exactly the same K groups, but the class of one is different because now I have to take a trace. And this is what gives you this complication, and this is what somehow puts the K into this equation. And the congruence relation is slightly more complicated, but not much so. Okay, so now we know that by Kirchberg and Phillips, there must exist a star homomorphism from OP to MK of OQ whenever this congruence is satisfied. So we wanted to repeat on one hand side what Kawamura did for embedding of Kunz into Kunz, and generalize of what we incidentally bumped to, the embedding of O2 in M2O3. So we asked the general question, can we do it? Can we write down explicitly these embeddings, employing our theory of functorial inductions from graph into graph sister algebras? And indeed, we managed to do it after struggling for some weeks. And this is our main result. If I take P, Q, and S, that satisfy the congruence relation above, and I want P and Q to be at least 2. I mean, you don't have Kunz algebras or 1, so P and Q must be at least 2. And now we claim that there exists a finite sequence of admissible graph homomorphisms, which I will explain what I mean by it, that induce injective unital star homomorphisms between their graph sister algebras, and when you compose them, lo and behold, you have a unital embedding of OP in MKOQ. And I repeat, it's very important that it's unital because when you skip the word unital, you have some trivial embeddings. Already in the Kunz paper, you can embed everything in some way which is non-unital. But we are talking about unital embeddings. And in fact, this congruence relation is interesting. You can draw some trees. I mean, things can embed it somewhere, but not everywhere. And in particular, you see, if you take n equal to, wait, should I? Okay, it should work. Oh, sorry, this is not on my screen. When you take n equal to 2, then this is 1. Of course, 1 divides any number. So you can take k exists, it's just equal to m minus 1. So this means that in O2, you can embed every Kunz algebra. Okay, so inside O2 sits any other Kunz algebra. But you can see from this congruence relation that here to have such an embedding, m is greater or equal than n. All right. Whereas here we kind of reversed it. We embed O2 in M2 of O3. So at the expense of adding matrices, I can now embed Kunz with lower index to Kunz with bigger index, but I have to take matrices. Yeah. Okay. And now this is what I want to prove. This is my main theorem. This is take-home message. And I want to prove it using functoriality of graph sister algebras, both covariant and contravariant. So to this end, I have to develop a little bit of a theory. I will not bore you with the definition of a graph. It's been done in previous talks. Just let me remind you that it's very important for us to know what the regular vertex is. And the regular vertex is a vertex which is not a sink and not an infinite emitter. So a regular vertex is a vertex that emits at least one and at most finitely many edges. Okay, and we denote all such vertices by reg of E. Finite paths are also defined. So let me not bother to do it again. I just want to draw your attention that I can very easily extend the source and the target maps from edges to finite paths by declaring that the end of a finite path is the end of its last edge, and the beginning of a finite path is the beginning of its first edge. And I'm pedantic about distinguishing between source and target maps extended to finite paths from these defined on edges, because every now and then I have to take pre-images. And when I have to take pre-images, it's very important whether I mean pre-images in finite paths and pre-images in the set of edges, okay? That's why I'm sort of so pedantic here about distinguishing between source and target maps from finite paths or from just the set of edges, so paths are like one. Okay, now I don't think it was explained, so let me do it very quickly. Whenever you have a graph, you can take its opposite graph. So basically what it means is that you reverse the direction of arrows, which formula is written in this definition. And now we have the concept of the extended graph. And basically, when you do the extended graph, you do what I wrote over here. You take a graph, you take its opposite, and you glue it over the graph, which consists only of vertices. So it has no edges, and these are the empty maps. Or in other words, you say that the extended graph is the graph which has the same set of vertices, E0 bar is equal to E0. But when you look at edges, you take the disjoint union of E1 and its copy. And its copy is denoted by the star. So these are sometimes called ghost arrows or ghost edges. And they are labeled again by E from E1, but they're written with stars. And the rule of the game is that when you take the source of E star, it's at the end of E, and the end of E star is the beginning of E. Okay, and this is how you get the extended graph. Now, this was not explained, I believe, and this is very, very crucial for my talk. So let me slow down a little bit here. What is the most obvious concept of a morphism between graphs? Okay, you have two set theoretical maps from edges, from vertices to vertices and from edges to edges. And of course, they have to respect the graph structure to deserve the name homomorphism. And this respecting the graph structure means the commutation with source and target maps. So it's irrelevant whether you first map your edge to another edge and then takes its beginning, or first take its beginning and map the beginning to another vertex. The same with endpoints, okay? So that's the most obvious concept of a homomorphism of graphs. You have the obvious category of graphs. And for instance, this category of graphs was successfully used by Stallings in his Invenciones paper, in which he proved using this category something spectacular about free groups, if I remember correctly. Okay, but when it comes to examples in non-commutative topology, like quantum complex projective spaces, Francesco was showing you as AF core algebras. Well, if you want to do some study CW complex structure and you want to have some pullback diagrams, the real life on topology shows you that this is not enough. And you need also morphisms going in the other direction. And what you find in textbooks is by far not enough, because you no longer can just assume that you map edges to edges. You still assume that you map vertices to vertices, okay? But now you can map an edge into a path of length 0, which is a vertex, or to path of length 1 billion. So basically, you say that you have a path homomorphism of graphs if you have a set theoretical map from finite paths of E into the finite paths of F, which, as I said, map vertices to vertices. Of course, you still have to respect the endpoints and the start points. And now here we have this nice condition, which somehow can be easily explained in terms of categories. Namely, if you can concatenate two paths PQ into PQ, then you demand that f of PQ is equal to f of P, f of Q, and f of P, f of Q again is a path simply because of these conditions that you have over there. Okay, and a very succinct way to understand it is the following. If you think about a graph as a small category, where vertices are objects and finite paths are morphisms, then basically what I'm telling you here is that it's a function between two small categories. Yeah, and this is exactly this functorial property. Okay, and it's very important that you observe as an elementary but important observation that if you want to see homomorphisms of graphs as special path homomorphisms of graphs, then you simply have to demand that says if and only if. So a path homomorphism of graphs is a graph homomorphism if and only if it preserves the length of paths. Okay, So the only difference between the lower and the upper definition is that in the lower definition, we forfeit the assumption that the length of paths is preserved. Because, of course, with this respecting of endpoints and start points, you immediately, these two maps induce a map from finite paths to finite paths. That's obvious. And because you map edges to edges and vertices to vertices, you preserve lengths. Here, you just preserve the zero, but nothing more. And just the case of notation, the first category we denote by OG, and the second category we denote by PG. Okay, but now that's not enough. I want to chisel some more interesting categories inside these big ambient categories. And I'm going to have two situations, the contravariant situation and the covariant situation, because the name of the game is the following. I want to find a category of graphs such that when I apply a contravariant factor, it gives me a star homomorphism between graph hysteralgebras, and I want to have another category of graphs. When I apply a covariant factor, again, it induces star homomorphism of graph hysteralgebras. Okay, and these things are constructed independently, and well, 1 hour is not enough to tell you about what we are doing now together with Gilles and Francesco, because we combined it into one relation category. So now we have a common denominator. But this requires an extra half an hour, which I don't have. So let me skip it. It's not essential for the problem that we solved with Yang Liu. Yeah, I forgot to mention it was written down, but it's based on my joint work with Yang Liu. Yeah, it simply happened that we had many dinners together in Trieste, and when we waited for pizza, we were calculating. This is how it came into being. All right, so now we are going to have, in each case, contravariant and covariant, we want to have three conditions. Why? Because the first condition ensures that you have a functorial induction on the level of path algebras. The second condition, which combines the first and the second, will give you, so I'm keep on restricting the categories. And remember, for me, graphs are arbitrary. They are not row finite. They can be infinite. They can have things, whatever you want. I'm completely democratic when it comes to graphs. All graphs are welcome, okay? But what we restrict, what we chisel in are morphisms, because we want to get only these morphisms that induce star homomorphisms, okay? And in order to induce path homomorphism, to induce a homomorphism of path algebras, the only thing that you need in the contravariant setting is that your map is proper, so finite to one. It's discrete topology, so proper means finite to one, okay? Now, if you want to preserve the first Kunstkrieger relation, it already becomes a little bit tricky. And what we discovered is the following condition, which we refer to as the target bijectivity condition. And it tells you the following, that whenever I take an edge in F, okay, then I can take the preimage under F1 of this edge. So now this is some subset of E1. These are some edges in E1. I take an edge in graph E, which is mapped by F1 to X. Then I take its endpoint, okay? And of course, by this graph homomorphism property, this endpoint must be the preimage of the endpoint of X. So in other words, F0 have to map the endpoints of E to the endpoint of X, right? And now I demand that for every X, this map be bijective, okay? So let me draw you some examples to somehow make it more explicit. Okay, can I click it? Yes. So what it tells you is the following, that if you take something like this, and you collapse it to just one edge, that's allowed. Because I identified two edges, but I also identified the two distinct endpoints. So V is allowed. What is not allowed is lambda. So if I have a graph like this, and I identify it like that, just one edge, okay, that's not allowed, because I don't have a bijection. I map one vertex to one vertex, but two edges to one edge. So 2 and 1 are different numbers. This is not bijective. And well, because we were in Arizona, Mariusz was speaking to John Quick, and John Quick was using things like pullbacks of the sets of edges and vertices in the more general context. And when Mariusz had the brilliant insight that, in fact, this set theoretical condition, let me switch back to my pointer. Oh, sorry, I keep on forgetting that this is not the touch screen. So this not very nice looking set theoretical condition can be in fact equivalently phrased in terms of the following condition, which is very categorical. So one can easily prove that the target bijectivity condition is equivalent to the commutative diagram being a pullback diagram in the category of sets. Okay, this diagram is always commutative because that's a property of the graph homomorphism that we have such commutative diagrams. We have one commutative diagram for targets, one commutative diagram for sources. So take this commutative diagram for targets and you demand it to be a pullback diagram. And lo and behold, you see that it's on the nose equivalent to this target bijectivity condition. And what is the upshot? Okay, so you have this category OG, and it's obvious that it's a category. Now, when I compose proper maps, of course, I get a proper map. But here, this is no longer so obvious, that composition of two target bijective morphisms, the target bijective morphism. But look, because we phrase it in such a categorical way, now, if I do, well, let me first erase it. Okay, now I get a pen. And imagine that I go to another graph G. So I have a map to G1. I have a map to G0. And I also have here a commutative diagram here, TG. All right? But this is the kindergarten of category theory. If this is a pullback diagram, and if this is a pullback diagram, then the rectangle is a pullback diagram, which gives me immediately composability of this condition. So I do have a category, okay? And now I have one more condition which I need, the regularity condition. So basically what I'm saying is that if I take the preimage of a regular vertex, then this must be the set of regular vertices. It can be empty, yeah? An empty set is a subset of anything, okay? So that's for preservation of a second Kunstberger relation. And now you can ask what on earth Katsura is doing here. Well,
what are we targeting, injective or subjective? Do you have an interpretation category?
Not really. I mean, this is a nice package, but yeah, I mean, look, when you really want to scrutinize the proof of this equivalence, you see, what you have here, okay, I have to go back to, I still have my pen. Okay. So here I have the pullback. So here's my pullback, right? And by the universal property of a pullback, I always have a map here, right? This you always have. The question is that it should be bijective. And it is bijective, and injectivity means, I don't know, target injectivity, and subjectivity means target subjectivity. So if you really want to split the hair into two pieces, that's how it is.
Because you also have a category where it's only required to be target injective.
No, this is why we don't bother.
I remember that. So from algebras target injective enough or something like that.
No. That's for con algebras. You have to have target bijectivity. What you don't have to have for conpav algebras is this regularity, because regularity takes care of a second Kunstberger relation which is non-existent in conpav algebras. Yeah, but if you want to split bijectivity into injectivity and subjectivity, this is reflected by this canonical map into the pullback. Okay. And now you can ask me what on earth Katsura is doing here. So we discovered these conditions during the pandemic. I had lecture courses, I had plenty of time, and I decided to dig into it as deeply as possible. Because you see, typically in the literature, what people used to study for decades is the following. You take a graph and you ask the question, when I take the subgraph, this inclusion of a subgraph into the graph will induce me contravariantly the C-star quotient from the C-star algebra of the bigger ambient graph onto the sister algebra of the subgraph. This is in textbooks. I mean, you have a number, hereditary, saturated, whatever conditions. It was incorrectly called quotient graphs. This is the most stupid terminology you can possibly fathom, because quotients are sister algebras, not graphs, okay? This was really bad, okay? But it's called quotient graphs. We call them admissible subgraphs, okay? So you should burn all the books that say quotient graphs, okay? But yeah, everybody spoke about subgraphs. So your morphisms were bound to be injective, okay? But I just showed you this Stolling's folding. I mean, Stolling's folding was very important in his famous paper. And this is by no means injective. Yet it does induce a star homomorphism, okay, contravariant. So we knew that there was somewhere there, and we discovered this target bijectivity condition, and we were very happy about it. But when submitting our paper to publication, Mariusz discovered that many, many years earlier, I don't know, like 2007, Katsura discovered the same formulas in the context of topological graphs. So when you take Katsura's condition and you choose your topology to be discrete, then you get on the nose our conditions, which is kind of funny because this is an immediate observation. You can do it on a napkin or in your memory, okay? But what you'd think should be obvious, imagine I take my conditions spelled out over there, and now I assume my morphism to be injected. I should immediately recover the conditions for admissible subgraphs. Well, you don't. I mean, you can prove it, but it's a theorem, I mean, proposition. Yeah, this is funny, that something which you expect to be obvious is not obvious. So, but it's good news because it means that to go beyond injectivity, you have to somehow really reformulate your conditions so that they really make sense when you are no longer injected. Okay, that's typically what happens in non-commutative geometry. You have a feature which for commutative sister algebras you can formulate in 100 million different ways, but only one of them will work when you go non-commutative. Yeah. Think about defining the quantum group inverse, right? And you need cancellation property in order to phrase. Okay, so that's somehow it worked here, and this is and on the other hand, we were of course disappointed that Katsura discovered it so many years before us, but we're also happy because if somebody else in a more general context discovered exactly the same conditions, they must be right. Okay. And he did not discover this beautiful pullback formulation. So at least we managed to beat him in one aspect. Okay, now how about the contravariant part? All right, so here, as I told you, the main upgrade is that we no longer assume that the length of morphisms is preserved. All right, so the first condition that we have is that you have to be injective on vertices. And because this is for covariant induction, it's quite obvious. Even in the path algebra, you have vertices correspond to mutual orthogonal projections or idempotents if you have no star structure. Okay, and it's obvious that if you have mutual orthogonal idempotents, you cannot collapse them to one. Yeah, because you would map something 0 to non-zero, and that's not allowed. So injectivity is necessary because vertices on vertices because they stand for mutual orthogonal. They label mutual orthogonal idempotents. Okay, and you cannot map two different mutual orthogonal idempotents to one idempotent. This would be impossible. Okay, so this is just to give you a covariant induction from path algebra to path algebra. But now, how about the first configuration to have path algebras? Well. And I know what I still forgot something to do. So I did not define for you what it means with order relation over here. So let me write it down right now. Okay, so when is a path alpha, finite path alpha less than equal to a finite path beta? Well, it happens if and only if there exists a path gamma such that beta is an extension of alpha by gamma, but you extend to the right. It's very important. You don't extend to the left, you extend to the right, okay? So f of E and f of E prime are finite paths, and if f of E prime extends f of E, then E must be equal to E prime, okay? And now, one remark that this is, of course, equivalent to saying that E is less than equal than E prime. I mean, because an edge can extend an edge if and only if it's equal to this edge, right? Because then gamma must be the end vertex, okay? So before in our paper with Alex Kirvasitu, when we studied mixed pullback theorem, we had the condition that we simply have monotonicity. That if f of p is less than equal than f of q, then p is less than equal than q for paths. But we found an example where this condition was too strong. And when I realized that I have to restrict this monotonicity only to edges, okay? It's kind of like we tried to define this relation. When we did it for paths, it didn't work. We had a counter example. When we did it on edges, we found the relation. Okay? Yeah, anti-monotonicity, okay. Reverse monotonicity. Yeah, okay. So you see, that was sort of the improvement over what we had with Kirvasitu, but that's not an interesting relation over here. So that's kind of very easy reverse engineering. When you want to see the first conspicuous relation satisfied in the covariant induction, you just unwind it and you see this. Okay. But now what is really breathtaking is the regularity. Okay. So this looks like some legal document, right? It looks like written by a lawyer. Yeah, but you can cite some Supreme Court verdicts from 1988, and if you take this clause and that clause, things work. We were somehow forced at the end of the day to write it in the way which is comprehensible even to the artificial intelligence. But for a human brain, it's kind of a mess. So please allow me to explain it in a human way. I will simply draw you a picture, okay? But if you really want to do proofs, this formulation that I gave you is better because you don't wave your hands, you just compute, okay? And it's much better, much convincing, and much more bulletproof, okay? So I'm just saying that it would take me too much to explain all this fine print, the legal stuff. I want just you to grab the gist of the idea. And by the way, I want to show you here how this regularity conditions forces on us formulas that were discovered by Kawamura. Okay. So how does it work? Well, imagine that I have a regular vertex V, and I have a regular vertex F of V. Okay, let me have here n edges. And let me have here m edges. And it's important when n is greater or equal to m, okay? So in the usual setting where edges are mapped to edges, well, if you open a textbook, it tells you, all right, m must be equal to n, and you map this set of edges to this set of edges, period. Otherwise, the second conspicuous relation is violated. But this is not what happens in real life. I mean, non-cognitive topology dictates you more fancy maps, okay? And also Kunz algebras dictate to you more fancy. So how do you do it? I mean, remember that I don't have to map edges to edges. I can map edges to finite paths. So the rules of engagement is the following. I take my set of m edges starting at f of v, and I take some of them, can be the empty set. I take some of them into my bag and declare them, okay, these guys are in the image. But all other edges are too short. I want to extend them. But the rule of engagement is that if you extend an edge, you must extend them by all edges that come out of here, all of them. There's no other way. So they're also regular. Yeah. So you cannot extend just some edges, but not by all edges. You must extend by all edges that begin at the end of the edge that you extend, or a path that you extend. So now you have paths of length 2. And now you repeat the procedure. Some of these paths of length 2 you keep and you throw them into the back, and for others say, no, they are too short. I want to extend them forever. And you do it as many times as you want to. And at the end of the day, you must arrive at n paths and you declare, okay, so this is my bijection. Okay. And let me show you how beautifully it works for Kunz, how it gives you on the nose Kawamura's formula. Okay, it will be more convenient for me instead of drawing n loops and m loops. Let me just draw n edges and m edges. But remember, these are loops. Okay, so I just have to have pen again. Okay. So again, oops, what have I done? No, it should work. Now I'm embedding OM in ON. Okay, so here I have M edges I have M edges, M loops, in fact. Okay, and remember that M satisfies the congruence relation. M minus 1 is equal to N minus 1 times K. Okay, and on this side, I have N edges. So what do I do? I take I divide my set of n minus 1 edges. So imagine that I take the first n minus 1 edges and I divide it into k subsets, disjoint subsets. So I take first n minus 1 edges and I map them into the first n minus 1 edges here. That's it. But then when I take the second batch of n minus 1 edges, I take these n minus 1 edges, extend it by all these loops again.
Which one is that? N is on the right.
Sorry, yes, my handwriting is a bit rusty. That's N. Yeah.
So you take N minus 1 edges.
No. I still have M edges and N edges. It's just, I'm just, the congruence relation is, if you want, like this. I write M as N minus 1 times K plus 1. I'll have one base path. Okay.
But on the left, with the left.
Yeah. I have N minus 1 and minus 1 with K times, and I'll see one edge left. And I will map it to a special path. Okay. Okay. So the second batch of n minus 1 edges, I map into paths of length 2. And I continue like this. Okay. So I go here, and I extend all these again by all the loops. I have to do it. Okay. I extend it like this, and when I take these paths, I take paths of length 2, and I extend the rest, and I continue doing it like this until I do it k times. Yes, I do it k times, and this way I obtain n minus 1 times k paths, and I have one base path over there. So this gives me exactly a matches. And when you know the formula for the covariant induction, which I will show you in some forthcoming slides, then you see that this is on the nose of Kawamura's formula. So by knowing the regularity condition without looking up Kawamura's formula, I derived it. You know, in Italy, you have this nice tradition that you have a big sheet of paper before dinner, then you can flip it over and write it. So that's what we use to derive this. Yeah, and when you look up Kawamura, and of course, it's the same. Okay, so this is the regularity. Now, the construction of path algebras is very simple. You take a graph, you take all these finite paths, and well, you look at the path algebra. Now I should have my highlighter again. Oops. Yeah, and you simply take all finitely supported maps. Oops, sorry, this should be a highlighter, not a pen. I take all finitely supported maps from the space of paths into my ground field. So I have the obvious basis. Every path gives me a basis element, and multiplication is given by concatenation. Okay, so that's the construction of a path algebras. And now, in order to go to Levitt path algebras, you do the following. First, you take the extended graph, which I explained to you. You take the path algebra of the extended graph. Okay. And then you divide it by these two types of relations, the Kunz-Krüger relations of type 1 and Kunz-Krüger relation of type 2. If you divide just by the first set of relations, what you get is so-called conpath algebra, but let me not go into it. Okay. And and here you can see the formulas which Francesco was writing for regular vertices. It all comes from here. But my point is that if you introduce Levitt-Pav algebras like this, then you can introduce graph sister algebras like that. So for starters, let me take my ground field to be complex numbers, and these ghost edges provide me with a beautiful and natural star structure. So when I take my path algebra of extended graph or my Levitt-Pav algebra, I can say that the star structure is given by declaring that idempotents are self-adjoint, okay? So chi of V star is chi of E. And when I take the adjoint of chi of E, where E is an edge, then this is chi of E star. Remember, when we are talking about the extended graph. And then star of chi of E star is chi E. So these formulas give you a star structure on your algebra. So you have a complex star algebra. And then you can take the universal sister algebra of a star algebra. And if you take the universal sister algebra of Levitt-Pav algebra considered as a star algebra, then what you get is by definition a graph sister algebra. And note that I didn't have to write here this ugly subprojection condition, and also I didn't have to write what Francesco wrote, because Francesco wrote that the beginning of an edge times an edge is an edge. I don't have to write it because I'm starting from the quotient of Pav algebra, where this is the first relation I have. Okay? So I like this way of introducing graph sister algebras because it's very systematic and it's in line of the conditions as we were deriving. Okay, and now again, here we have a triple because Katsura also derived the first formula. So in the context of topological graphs, Katsura also had this formula. So I have to add them to this theorem. It had nothing to do with the second one. Okay, so now the theorem is the following, but if you have arbitrary graphs and G from F to E is an admissible graph homomorphism, so the lengths of paths are preserved. And by the way, preserving the length of paths means that the induced star homomorphism is gauge equivalent. So gauge action was defined, so you know what it is, okay? And if you take F from E to F to be an admissible path homomorphism, then you have two factors. So first, you can look at the first formula, and it defines for you a contravariant factor from this category of admissible graph homomorphisms to the category of sister algebras and star homomorphisms. And here, this is actually gauge equivalent, so you can talk about U1 sister algebras, and also if you have finitely many vertices, then you map Unital to you have Unital star homomorphisms because the preimage of all vertices must be all vertices, because you know that vertices are mapped to vertices. Okay, so that's the first formula, and well, I mean the formula is obvious. You take an edge or a vertex, and then you look at the preimage. So either have some finite set of edges, or you have, because we are finite to one, remember, we are proper. So either have some finite set, and of course, if it's empty, write 0. Sum over the empty set is by definition 0. Okay. So if P is not in the image of G, forget it. This is just you kill this projection or a partial isometry. Okay, and now if the set is non-empty, it must be finite, and then you take all these edges or vertices, and here you sum either projection or partial isometries, depending whether you have a vertex or an edge. Okay, and it's really a pullback, because if you look into the definition of Pav algebras over here, right? These are function algebras. So if I have a map from FPE to FPF, of course I have a pullback map going the other direction as long as my map is proper. Okay. And simply this pullback map goes to the quotient when you have other conditions satisfied. Okay. And when you compute what this pullback map really is, you get this nice form. Okay. So it's really a pullback like in differential geometry. Pullback not in the sense of diagrams, pullback in the sense of maps. Okay, and the other formula is even simpler, because what you have here, you have a vertex or an edge, and you must map a vertex to a vertex. So here projection will go to a projection, but if P is an edge, it can go to a path here, right? So this will be a partial isometry associated to a path, not to an edge. And when all conditions are satisfied, lo and behold, we have a covariant functor from the category of admissible path homomorphisms of graphs and to the category of sister algebras and star homomorphisms. But here you are no longer unital in general. Even if you have a star homomorphism between unital sister algebras, we are no longer unital. And it's very easy. I mean, think of embedding M2 of C into M3 of C. This is a non-unital embedding. It exists. Okay, I can map one path to another path. I have an embedding, but it's non-unital. Okay, so now with this technology at hand, we can go and prove our main theorem. But first, we have a commercial break. There is no free lunch. And somebody pays for Francesco and I being here. And this somebody is the European Union. And we have a huge project called Graph Algebras, which spans the period of, oops, what have I done? Oh, no. I think, Jules, you have to help me. I touch, okay, so I still have to share. Okay, so you'll do it faster. Sorry. But I can keep talking. So we have a network of 26 research institutions combining together about 80 mathematicians. 11 institutions are in Europe, including Israel. And we have money to travel to our partner nodes, which are by definition located outside of Europe. And we have 15 of such institutions. And I'm very happy to say that as a result of a recent amendment, we replaced universities in Kansas by this university here in Florianopolis and by a university in Sydney. So we traded Kansas for Brazil and Australia. I think it's a very good deal. We have much more territory. Okay, so we are expanding. So this is what is highlighted here. I'm from IMPAN, Francesca is from Naples, and well, Gilles is from Santa Catarina. So here we are. And this grant pays for our visit here. Okay, unfortunately, the funding is only one way. I mean, we can come to visit you, but we have no money to pay for you to visit us. But we had a lot of money the previous year, so Gilles, Nata, and Paula visited us in Warsaw, and I hope you guys get fun. And now you are supposed to apply for some Brazilian matching fund. Okay, so he might get the money for you guys to come again to Warsaw. That's so be good to him. Okay. All right, and of course, Gilles is the node coordinator, so he is in charge of Florianopolis. Okay, now in this slide, I need only one thing. I need only, oops, again, I'm doing something. Okay, I want this. Okay. All I need is that the Kunz algebra is nothing else but the graph sister algebra of a Hawaiian hearing graph, which again was used by Francesco. But I cannot refrain from making a quick historical remark. You see, Levitt, Mr. Levitt, Professor Levitt worked on his algebras in '62, so it was before I was born. And of course, he would never recognize Levitt path algebras, kind of like Dirac would not recognize Dirac operator used by Alan Kohn. But this name Levitt path algebras came from somewhere. So you see, what Levitt was interested in was this IBN thing. So he was looking for some universal rings with the property that if you take a ring, and when you take its nth power here, and you take its nth power there, these are isomorphic as modules, okay, as modules, which is remarkable because it means that in general, there's nothing like the rank or dimension of a free module, okay? You don't have this invariant basis property, okay? And then you can ask, what is the universal ring which has such a property? And these are the Levitt algebras with indices m and n, okay? And over some field k. But now if you specify your m to be equal to 1, so you're asking when a ring is isomorphic as a module with Rn, lo and behold, this is exactly the Levitt path algebra of a Hawaiian hearing graph. Okay, so this is how people who started doing Levitt path algebras in 2004 baptized it as Levitt path algebras. Okay, And you can immediately see from the obvious calculations that indeed you have this isomorphism. LK1 n to n is isomorphic with LK1n because of these formulas. You can have easily a module isomorphism given by these formulas. But I don't need it. This was just a historical remark that Kunz algebras are interesting and have nice roots, not only in some Markov chain processes Kunz and Krieger were interested in, but also in some purely algebraic things. Okay, but now let's get to the proof. And this is the highlight of my talk. This is the take-home message. If you have to remember one thing from my talk, please remember this. Okay, I call it the art of graphs, because the name of the game, what we are struggling with young Liu to do in Trieste, was precisely to discover this diagram FMN. Oops, I should switch to a highlighter. All right. So what happens here is the following. Remember, we want to embed Kunz algebra into matrices of a Kunz algebra. All right. So for starters, what is a graph of the sister algebra of matrices of a Kunz algebra? Well, you can very easily convince yourself that if you take the sister algebra of this graph and you just play with generators and relations, you can very quickly see that it's on the nose isomorphic to the sister algebra of K by K matrices over the Kunz algebra OM. And remember, we are working here all the time under the assumption that oops. Oh no. Okay. 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 That m minus 1 is in congruence with n minus 1. So n minus 1 divides m minus 1. Okay, so this is our assumption. So, all right, and now you can ask, well, how do we do it? Well, there is some general theorem, and I think Francesco was exploring it in his talk, that if you have a graph sister algebra, and if you want to have matrices over this graph sister algebra, you modify graph by adding some edges. Okay, and Francesco used it to have matrices over the circle. Okay, but this algorithm is kind of ugly from our point of view. It gives us graphs that we don't want. It introduces sources, and you know, we can do it in a better way. In this case, at least. Remember, the theorem is general. So you see, basically what we do here, we say, okay, here is just a point, but I can blow this point to a path of length k. And if I blow this point to a path of length k, I get matrices. And this is what this Lauer diagram GMK is. Okay, I blew the point into a path, and just by direct calculation on generators and relations, I can prove that these are matrices of a Kunz algebra OM. Okay, so that's not a big deal. But the problem is that when I look at this bottom graph, I don't know how to relate it to the Hawaiian Ewing graph. I don't know how to get the embedding. Okay, so what we did was the following. Well, we take the sister algebra here of this graph, and I claim that this is isomorphic with this sister algebra. So this gives me just a different presentation of matrices over Kunz, but I want to argue how I get it, right? And I get it by the covariant induction. So here I have a path homomorphism of graphs, okay? How do I do it? Well, I map black edges. Vertices go to vertices by density, okay? Now I map black edges to black edges. Well, almost, because here I have this black edge EM, and what happens on this side that I have too many red edges, all right? But I have this congruence relation. So what I do, I take this edge EM outside, then I have exactly m minus 1 edges, and I can divide m minus 1 edges into k disjoint subsets, each of them having n minus 1 edges. Okay, so I split my m edges into k plus 1 subset. One subset has one edge, that's EM, And then K subsets have exactly n-1 different edges, and the set is disjoint. And now how do I define my path homomorphism? Well, when I look at all these red paths that go from VK to V1, well, I go by identity here. Yeah, I take my first batch of n-1 many edges, okay? But now, how about these n-1 many, because it's not written here, it's written at one place, but it should be written everywhere. This is n-1 edges everywhere, okay? But now when I take n-1 edges ending in V2, remember, I have to preserve the endpoints. So I cannot map it to red edges because they have different endpoints. Well, but I do the obvious thing. I take the next batch of my n-1 edges and I extended them by this edge. So I have a path of length 2, okay? And so on and so forth. And at the end of the day, in order to have these n-1 many loops, what I do, I take these n-1 many remaining edges and I compose it with this path of length k, okay? And you can easily convince yourself that all conditions are satisfied. Most importantly, I'm injective on vertices because I'm bijective. The target, sorry, this is covariant induction. So the next thing to be satisfied is monotonicity. Again, it's not a problem because each edge is mapped to a path which starts at a different edge. So no path which is the image of an edge is an extension of another path. So monotonicity condition is immediately satisfied. Okay, and then the final regularity condition, it is easily satisfied because you see, while I'm extending my paths to be longer and longer, I always look at vertices that emit only one single edge. So I do extend them by all edges coming out of this. Okay, so regularity, this tricky condition, is satisfied. So I have a legitimate path homomorphism from the graph FMN to the graph GMK. And it's kind of trivial to see that this is an isomorphism. Well, I mean, for starters, we have a simple sister algebra, so it has to be injective. And to see that you have all generators in the image, so you have to be subjective. Okay, so it's obviously, and you also can immediately write explicit universe. But let me get back to it in a few seconds. But now, how about this graph? Where do I write it? This graph here, the Kunz graph. So I have here n loops, okay? N loops, and here's my Kunz algebra, all n. Well, I'm missing this star homomorphism, yeah? But here I can apply contravariant induction because the beauty of this graph, this is what we're searching for, is that I can collapse this graph to the Kunz graph, okay? And what is the major difficulty? It's target bijectivity, okay? Everything else is kind of easy. Preimage of regular is regular because all vertices are regular, so that's not a big deal. What else is there? Finite to 1. Graphs are finite, so we are finite to 1. The only non-trivial thing, this is why we couldn't use the diagram GMK, which was obvious from the point of view of matrices over Kunz. The only thing which is subtle is this target bijectivity condition. But because we have this graph was custom designed to make the target bijectivity condition fulfilled. So for starters, what do I do? Here I have n loops, okay? And here I have very many edges, okay? How do I collapse? Remember, I have to collapse as many edges as many endpoints. So imagine that I take all black edges. Each of the black edges ends in a different vertex. So I have exactly k, yeah, I'm right. I have exactly k different edges, each of them ending in a different vertex. And what do? I collapse them into the first loop because it's obvious I collapse all edges to the unique edge. I have no choice, okay? And target bijectivity is satisfied, yeah, because I collapse as many endpoints as edges. And then I continue. Because of this congruence relation, what I do is the following. I have k batches of red edges, okay? I have k of them, something which ends in V1, V2, and Vk. So I have 10 batches of n-1 edges. And what I do, I apply the axiom of choice. Out of the set of n-1 edges, I choose one edge, Then from another subset, I choose another edge, I choose k edges, each of them ending a different vertex. And what do? I collapse them to yet another. And I continue doing so. And this way, finally, at the end of the day, I collapsed all of this into n different loops. Because the first one, the collapsing of the black guys give me the first loop. And then the collapsing of the red guys gave me n-1 loops. n-1 plus 1 is on a good day n. So this is how I now have a contravariant induction from On into Mk of On. So now we are ready to prove the main theorem. So now I take my natural numbers P, Q, M, N, and K, 5 of them, to first P and Q, M, and N are at least 2 because they are indices of a Kunz algebra, so they have to be at least 2. K is like the size of a matrix, so it's okay for this to be at least 1. And now I assume that the following 3 congruences are satisfied. That's my first congruence relation. That's my second congruence relation. And this is my third congruence relation. Okay. And when I have these congruence relations satisfied, okay, I explain to you how I get a graph homomorphism from Fmn to En. I explained to you how I have path homomorphism of graphs from Fmn to Gmk, okay? And they induce contravariant and covariant respectively, unital star homomorphisms between graph sister algebras, okay? So this way I can go from Kunz On to Mk over Om, okay? But so I'm almost done, but not quite yet. Remember that I had this general Kunz, that I had this general congruence relation, which was the maximal congruence relation allowed, I mean, the most general congruence relation allowed by K-theory. And I want to exemplify the Kirchberg-Phillips theorem. I want to prove that whenever K-theory allows, I can actually construct a star homomorphism, okay? So I have just one more step to do, but now I use Kawamura's embedding, okay? Now, using, okay, here to have an embedding, Kawamura's embedding of OP in On, I have to use this congruence relation, right? That's for embedding OP in OM. Now, for embedding OM in OQ, I need this congruence relation. And the middle congruence relation I just used for what I explained to you, right? This was from the previous slide. This was the art of graphs, okay? But now, of course, you can amplify if you have an embedding, Kawamura's embedding of OM in OQ. Of course, you can go by identity on matrices. So you have an embedding of MKOMN in MKOQ, right? So this way, I'm giving you a sequence of unital star homomorphisms of graph sister algebras. And when I combined all of them, I get exactly what I want, an embedding of OP in MKOQ, all right? So the only thing which I have to do to finish with, I have to somehow argue, why does my general congruence relation imply these 3 congruence relations? But this is completely trivial. Remember, the assumption of the theorem is this congruence relation, right? And I have to show to you that this congruence relation implies, as a special case, the 3 congruence relations that I'm using in my construction. But it's obvious. I take R equal to S, I take L equal to N, I can N equal to P, and the only thing which is a bit tricky, I have to take M equal to Q minus 1 times S plus 1. When I make this substitution into my congruence relation, I obtain these 3 congruence relations. So all these maps exist. Yeah, I constructed them. And the reason why I claimed in my abstract that these are polynomial relations is because if you look at these formulas here in this functoriality theorem, you see what happens in the first case is that you have generators and you map them into sum of generators on the other sides. But the generators have to have the same power, right? I mean, generators to sums of generators, but no powers. And here you take generators and you cannot map them to sums. There are no sums. But you can map them to any powers. And then you can have Yn, Zm, right? These are monomials, but of arbitrary degree. Well, now when you combine 2 of them, you have polynomial expressions of generators. Okay. So not only I give you an explicit formula for embedding, for arbitrary embedding of Kunz into matrices over Kunz, but I give it to you in terms of simple polynomial formulas. And that's the main result of my joint work with Yang Liu. And let me stop here, apologizing for 5 minutes overtime.
Do you get anything new at all if you look at the homomorphism from matrices to matrices of the solvers?
You mean matrices of different sizes, right? Yeah, I guess you could play this game, but I don't believe you could get anything new, because you see, okay, you can consider it, right? Of course, you can consider it, but somehow we stopped here because if you can embed in Kunz over matrices, and when you take matrices over Kunz in the domain, when you take matrices over there, but you are right, you can ask a more general question. You can say that you want to vary the sizes, and you can ask again what K theory allows, and you can build it. Yeah, this is a very good question.
So,
yeah, you might be right. You might be right. This can give you something slightly more general. You might be right, but I'm certain that you can solve it using the same technology over here. Yes, I presume you're right. Yes, it's an excellent question. Thank you so much. Yeah, that's maybe what we'll do after we finish writing it up. Yes. Because the thing which I told in my morning talk in Göttingen, where I had 90 minutes, was that we combine these covariant and contravariant inductions into just one relation. So instead of having a map from one graph to another, or from another graph to the first one, we just have a relation. And this allows us to combine these things. So instead of writing a sequence of relations, I could just write, hey, a sequence of morphism, I have one relation morphism. And this is just one relation. I have one functor and one relation, and it's much more beautiful. But there is obviously a need for having a relation. Well, here I gave you something very specific, Kunz, matrices over Kunz. But we're playing around the other day in your office, in Gilles' office, just with understanding of how to prove that if you have different graphs giving you matrices over complex numbers, how to prove that these are always matrices over complex numbers. And it turned out that if you really want to write it down explicitly, we need both. You need a relation. You cannot do it by one graph homomorphism. You need contravariant induction and covariant induction at the same time. And when you combine them, it's a relation. So relations allow you even to understand something as simple, obvious, and fundamental as why you can write matrices over complex numbers in many different graphs. How a relation allows you to understand it tangibly. Oh, Piotr, wow.
Piotr again?